This video will discuss all 7 active volcanoes within the state of Washington, even the lesser known ones, with each volcano and their last eruptions being discussed, beginning at the timestamps shown on screen. Enjoy! The state of Washington contains 7 volcanoes which are classified as active, the last of which erupted between 2004 and 2008. However, Mount Saint Helens is not the only volcano which has erupted quite recently, as there is also a towering glacier-covered peak which erupted approximately 324 years ago. The peak in question rises to 3,213 meters or 10,543 feet above sea level, and due to the fact it contains more than a dozen glaciers is referred to as Glacier Peak. Along with Mount Saint Helens, Glacier Peak is the only volcano in the state of Washington to have produced multiple powerful plinian eruptions during the last 20,000 years, some of which were larger than the infamous 1980 eruption of Mount Saint Helens. As a result, much like Mount Rainier, Glacier Peak has a large potential lahar risk area since much of its glaciers could melt during a future eruption, placing up to 67,000 people at risk of being inundated by lethal lahars up to 71 miles away from its summit. The Glacier Peak volcano can be found in north-central Washington, where it is centered 65 miles east-northeast of the city of Seattle. Like other volcanoes in the Cascade Mountain Range, Glacier Peak exists due to the offshore subduction of the Juan de Fuca plate underneath the North American plate. The subducted oceanic crust from this collision then experiences partial melting, rising upwards to create magmatic intrusions which goes on to form a chain of volcanoes. If you look at Glacier Peak from satellite, you will note that it has an incredibly rugged appearance. Although this is partially due to explosive volcanic activity, it is primarily due to numerous glaciers which have carved out large portions of this mountain. Due to the numerous glaciations this volcano has experienced, much of its early geologic record is not well known. What we do know is that this volcano began forming sometime between 600,000 and 200,000 years ago, as this marks the age of its oldest radiometrically dated lava flow. These earliest eruptions were remarkably similar in composition to its more recent eruptions, creating mostly volcanian eruptions which interwove thick, slow-moving viscous dacite lava flows with layers of ash. These early eruptions built a central, albeit rugged volcanic cone, which was soon carved away by multiple cycles of glacial advance and retreat due to the ongoing ice age. The layers of ash were far more susceptible to erosion than the harder dacite lava flows, resulting in the vast majority of ridges going away from Glacier Peak's summit representing high points on past viscous lava flows. As Glacier Peak continued to grow, with vents largely aligned along a north-to-south trend, not all of its eruptions originated from its summit. 3 such eruptions during the last 50,000 years create a series of separate cinder cones and spectacular strombolian eruptions, emplacing lava flows that follow the low points and glacially carved valleys. The youngest of these vents is the White Chalk Cinder Cone, which may have formed in a moderately explosive eruption around 15,000 years ago. After glaciers began to retreat after the last glacial maximum, the most energetic period known in the lengthy history of Glacier Peak occurred. Specifically, between 13,073 and 9255 BCE, a total of 6 highly explosive eruptions occurred, 4 of which are plinian in nature, reading in on the Volcanic Explosivity Index as a 4 or 5. These eruptions not only caused ash to accumulate in 3 states and a portion of British Columbia and Alberta, but also generated pyroclastic flows that reached as much as 6.5 miles away from its summit. These pyroclastic flows melted large volumes of glacial ice, creating lengthy lahars that would inundate areas up to the edge of the Pacific Ocean. The largest of these eruptions emplaced 6.5 cubic kilometers of tephra, 5 times larger than the 1980 eruption of Mount Saint Helens. After a long pause in eruptive activity, Glacier Peak's eruptions resumed around 6,000 years ago, going on to produce 6 eruptions in the time since. 5 of these eruptions built lava domes that partially collapsed numerous times, generating numerous pyroclastic flows. The most recent eruption took a break from this pattern, involving no lava, but instead explosive activity involving expanding steam and volcanic gases in what is known as a phreatic eruption around the year 1700. While Glacier Peak has not shown any signs of unrest since then, there are still reminders that underlying magma exists here due to the presence of multiple hot springs on its flanks. As a result of the many future hazards a future eruption of Glacier Peak could pose, the U.S. Geological Survey assigned this complex as a very high-threat volcano. Hidden in the forest southeast of Mount Saint Helens are a series of lava tubes, shield volcanoes, volcanic features which formed under a thick glacier, and a singular young lava flow of a very large size which covers approximately 19.5 square miles. All of these features and more are part of a technically still active volcanic complex which is frequently overlooked by the two towering stratovolcanoes to its north, being known as the Indian Heaven Volcanic Field. The Indian Heaven Volcanic Field can be found in south-central Washington state, where it is just north of the Columbia River, with the nearest community being the town of Stabler 10 miles to the southwest. The Indian Heaven Volcanic Field consists of approximately 70 vents spread across an area of 450 square kilometers. These consist of cinder cones, shield volcanoes, toyas, and a singular maar composed of low silica eruptive products that, although primarily composed of basalt, also on occasion contain basaltic andesite and andesite. Most of these vents are aligned along a single north-northeast facing line which is 17 miles in length. These vents all formed in moderately explosive eruptions, with the story of this field beginning approximately 700,000 years ago. That means that Indian Heaven was erupting long before Mount Saint Helens existed, or even before Mount Adams began to grow. So, 700,000 years ago, magma with an initially low silica composition was generated from the subduction of the one-day Fuca plate underneath the North American tectonic plate. This magma quickly intruded into the crust, eventually rising to just below the surface, causing an explosive reaction which expelled volcanic projectiles and created an ash-dense plume. As the magma continued upwards, the gases and volatile material within it quickly expanded, propelling the magma upwards until a several hundred-foot-high lava fountain was generated. This eruption slowly but surely built an 800-foot-tall cinder cone which produced blocky lava flows that moved towards the southeast. By the time this eruption had ended, the feature that we today know as Flat Top Mountain had been constructed. I cannot prove the following statement, but I have a suspicion that no further eruptions occurred in this part of the field because its magma was partially stolen deep underground and redirected into the underlying system that would form Mount Adams. Subsequent eruptions occurred about once every 10,000 years, primarily occurring in a dominant zone of weakness in the crust that had developed. Several 5-mile-wide shield volcanoes formed, including Red Mountain, so named because of the bright red scoria on its peaks which became visible after glaciation greatly smoothed its edifice. At least 7 major glaciations would occur across the lifetime of this field, and since the ice sheet at times was up to 500 meters or 1,640 feet thick, means that interesting lava-ice interactions occurred. As lava erupted into the bottom of this glacier, it could not travel very far and slowly built up into a steep-sided hill. Eventually, a large section of the overlying glacier was melted by its proximity to the lava, forming a small glacial lake. As eruptive activity continued, the volcanic cone eventually reached the height of the lake. Lavas then slowly deposited along the level of the lake water, forming a flat top. By the time the eruptive series had ended 130,000 years ago, what remained was a unique subglacial volcano termed a toya, today known as Lone Butte. During the last 30,000 years, this field was more active than average, producing 6 distinct eruptions. The youngest of these occurred in 6150 BCE, where 900 million cubic meters of lava was erupted from a central cinder cone over a period of 200 days. The deposit it formed is today known as the Big Lava Flow and is easily visible from satellite. While this volcanic field is unlikely to erupt anytime soon, a future eruption could generate minor disruptions to air traffic through Stromboli and associated ash emissions alongside lava flows potentially up to 29 miles in length. As a result of these hazards, the U.S. Geological Survey designated Indian Heaven as a low-threat volcano. 3 towering glacier-capped stratovolcanoes are visible from downtown Portland, Oregon. While both Mount Hood and Mount Saint Helens have erupted multiple times since the city was established in 1851, their taller counterpart, aka Mount Adams, has not. And yet, despite how quiet Mount Adams might appear today, it is not only one of the most active volcanoes in the state of Washington in recent geologic history, but also has the 4th highest number of Holocene eruptions in the entirety of the lower 48 U.S. states. With 15 confirmed eruptions during that time span, meaning an eruption about once every 780 years on average, it has produced a multitude of hazards. These hazards range from gas emissions during eruptions to long-traveling lava flows which can reach as far away as 9 miles from its summit, to even pyroclastic flows which can travel as much as 9.3 miles or 15 kilometers away. But by far the most significant hazard at Mount Adams are lahars, not only related to the glaciers that might partially melt during any future eruption, but also due to its highly weak and hydrothermally altered southwestern section. In the last 6,000 years, this altered region produced 3 major collapses, 2 of which inundated large swaths of what is now the modern community of Trout Lake, population 875 and up to 65 feet thick of debris, with one of these events possibly even having reached the Columbia River. Add this to the fact that 2 of these collapses occurred unrelated to an eruption, and that any future eruption, since all recent Mount Adams eruptions have had a degree of explosiveness to them, would disrupt regional air traffic. It should come as no surprise that Mount Adams is classified as a high-threat volcano, with 6,475 people living in its various hazard zones. And today, Mount Adams has produced a record number of earthquakes in recent months, although these figures are still fairly low compared to other volcanoes and we don't yet know their cause. Mount Adams is the 2nd largest stratovolcano in the entire Cascade Mountain range, with a volume of 300 cubic kilometers, only being behind Mount Shasta's 350 cubic kilometers. This large volume can be owed to both its consistently high eruptive rate, being fed by partial melting generated from a tectonic plate collision, but also its absurdly old age, with its cone having been growing since 520,000 years ago. But even before this cone began to grow, the region was already marked by scattered volcanism via what is known as the Mount Adams volcanic field since 940,000 years ago. These early eruptions formed scattered cinder cones and lava flows, many of which, albeit while highly eroded, can still be seen on the margins of the modern volcano. Yet, you might have noticed that several large vents are located on Adams's eastern side. This is no coincidence, as Adams's magma chamber is still to this day off-center to the east, with additional eruptions 520 to 460,000 years ago occurring 3.1 miles southeast of its modern summit. These initial eruptions were highly explosive, producing thick dacite lava flows and domes that the later volcano would build upon. Afterwards, eruptive activity shifted to its modern location beneath what would become the summit of the volcano. These early eruptions were moderately explosive but produced numerous lava flows, building an apron of lava flows that created a circular 18-mile diameter apron of material that filled in the rugged terrain from prior volcanic field vents and constructed the complete base of Mount Adams. Cone building followed, with overlapping layers of andesite lava and ash being in place during frequent eruptions across the next 459,000 years. However, while the main cone never became inactive, it entered unusually active periods approximately 500,000, 400,000, and 50,000 to 30,000 years ago, with the latest such period building the top 250 meters or 820 feet of its modern cone. During this time span, the flank shield volcano known as Goat Butte formed 150,000 years ago, and the Little Mount Adams cinder cone formed 67,000 years ago. The volcano entered a less active period for a time until, around 15,000 years ago, it produced a series of explosive eruptions that topped the volcano in a layer of tephra. After the end of the last ice age, 11 eruptions occurred from Adams's summit, never rating higher than a 2 on the 0 to 9 Volcanic Explosivity Index, although 4 eruptions occurred on its flanks, emplacing fairly sizable andesite lava fields, which each covered as much as 6.9 square miles. The next eruption from Mount Adams is likely to be moderately explosive and occur from its summit, but when this will occur is unknown, although statistics suggest sometime in the next 1,000 years. Approximately 3.72 million years ago, a towering glacier-top peak existed in the state of Washington. However, this mountain was a volcano known as Hennigan Peak and would soon collapse in a catastrophically large eruption, forming a nearly 5-mile-wide caldera. A second large edifice then grew over the following 2.5 million years 10 miles to the west-southwest, but this too would experience a catastrophic eruption and form the Kolshan caldera 1.15 million years ago. After eruptive activity paused, construction of the modern Mount Baker volcano began 6 miles further to the southwest, which has thankfully not experienced a caldera collapse in the years since. But given the history of its neighboring stratovolcanoes and its largely andesitic to dacitic composition with occasional rhyolite, it could one day in the distant future produce a similarly catastrophic eruption. Yet, this is not the only reason why this glacier-covered peak, which has historically been the second most active volcano in the Cascade Mountain Range, is considered so dangerous. Namely, because 1.8 cubic kilometers of ice lies on its towering edifice, and large sections of this could melt during a volcanic eruption, generating long-reaching lahars which could become several hundred feet high. In fact, looking at Mount Baker's hazard map, nearly 87,000 people live in a lahar risk zone, a figure only second within Washington state to Mount Rainier. 4 such large lahars were generated in the last 10,000 years, some possibly due to eruptions, others by non-eruptive processes. Taking this into account, alongside Mount Baker's recent high eruptive rate is why this volcano is classified as a very high-threat volcano. In fact, an intrusion of magma recently occurred underneath Mount Baker's edifice in 1975, but remained fairly deep and did not result in an eruption. However, while declining year over year, Mount Baker has still been degassing at an elevated level ever since via its fumaroles, so if you ever see a gas plume rising from this volcano, that will likely be why. Mount Baker and its surrounding region that includes the Kolshan and Hennigan calderas mark what are known as the Baker Volcanic Field. Volcanic activity in the last several million years has seemingly shifted southwestward over time, with Mount Baker only truly beginning to form 495,000 years ago. Like all other Cascade Range volcanoes, Mount Baker began erupting due to the subduction of the Juan de Fuca plate underneath the North American plate. The initial phase of activity at Mount Baker was marked by a combination of explosive volcanic eruptions which ejected ash alongside the emplacement of andesite lava flows. This initial eruptive center built a central cone that likely towered at least 1,000 feet higher than the modern Mount Baker, resulting in glaciers forming on its edifice. These same glaciers later almost completely eroded away the originally taller satellite cone, which is today referred to as Lava Divide. At the latter stages of Lava Divide's eruptions, andesite lava erupted at what would become the tallest peak of Mount Baker, with additional lava flows erupting all the way up to 366,000 years ago. The Black Butte satellite cone then became the dominant vent for a time, growing between 350,000 and 288,000 years ago. Around 140,000 years ago, with a tall cone to the northeast and another one to the southwest, was when Mount Baker's main cone became the dominant vent. However, its eruptions for the next 100,000 years were highly explosive, producing minimal lava and large amounts of ash and explosive eruptions, with this fact largely preventing the edifice from quickly growing. It wasn't until 40,000 years ago until its eruptions suddenly became less explosive that a major period of cone growth began. That means that yes, almost all of the summit area was created since then via more than 100 distinct explosive and effusive eruptions in that time span from the now buried Carmelo crater. Interestingly, a flanked cinder cone known as the Schreiber Meadow Cone formed approximately 10,000 years ago to the south of Baker's summit, generating a 12-kilometer or 7.5-mile long basaltic lava flow. However, all eruptions since 7,500 years ago have originated from a separate vent half a mile south of its summit at Sherman Crater. Several large lahars also occurred during this time span between 4700 BCE and 3800 BCE. Then, no additional volcanic activity was recorded at Mount Baker until 1820 when a phreatic eruption occurred on its summit. An eruption an order of magnitude larger occurred several decades later in 1843, generating a lahar. Following this, from 1846 until 1880, as many as a dozen additional small phreatic eruptions occurred from Sherman Crater. If Mount Baker was to erupt again, its most likely source would be from Sherman Crater. Of all of the active volcanoes in the United States, there's a single system which I hope to never see erupt in my lifetime. I do not mean the Yellowstone volcano in Wyoming or even the densely populated Clear Lake volcano in California. Rather, I am referring to the towering Mount Rainier, as a future eruption of this volcano in a worst-case scenario could cause tens of thousands of casualties and billions of dollars in damage. The reason why this towering peak is so potentially dangerous relates to one simple word: lahars. Per a direct quote from the U.S. Geological Survey, a lahar is a hot or cold mixture of water and rock fragments that flow quickly down the slopes of a volcano. They move up to 40 miles per hour through valleys and stream channels, extending more than 50 miles from the volcano. Lahars can be extremely destructive and are more deadly than lava flows. While this description might make it sound like lahars are simply a typical flash flood, what this definition leaves out is that lahars often overtop the river channels they are in and spread out to surrounding higher ground which is not ever affected by flash flooding, reaching heights of up to 50 meters or 164 feet and bulldozing everything it encounters. Lahars act like a fast-moving wall of concrete and since the beginning of the 16th century have caused approximately 56,000 fatalities at various volcanoes around the globe. Factors such as a tall volcano height, heavy glacial cover, and significant hydrothermal alteration are all factors which aid in the generation of lahars, and Mount Rainier has all three. Today, more than 150,000 people live and work on top of lahar deposits which Mount Rainier deposited during the last 10,000 years, and just so you can understand how significant of an area would be at potential risk were a volcanic eruption to occur, I have overlaid this map. The purple represents the area devastated by a lahar in the year 1500, the pink represents part of the area affected by a lahar around 100 BCE, and the largest of the group, aka the yellow, represents the massive Osceola lahar, which was produced in the year 3600 BCE. This is why if you live in Puyallup, Auburn, Buckley, or a select number of other local cities, if you were to dig down, look in a local road cut, or see a rock layer that is primarily brown but also a mixture of yellow and orange, then you are looking at an area impacted by this prehistoric Osceola lahar. This Osceola lahar material is partially composed of remains of Mount Rainier itself, as at the beginning of the explosive eruption which eventually formed this lahar, Rainier was 1,100 feet taller. This additional height is no longer present on Rainier as it collapsed as part of a massive landslide which generated the Osceola lahar. The good news is that such large-scale lahars generally but not always occur as the result of a volcanic eruption. And if Mount Rainier was to erupt again in the future, there is also a chance that no lahar or only a small-scale lahar occurs, which only impacts areas within Mount Rainier National Park. Among Cascade Range stratovolcanoes, Mount Rainier is quite an old complex as it began forming 500,000 years ago. Its first eruption occurred in the remains of an older, highly eroded stratovolcano that stood in its place between 1 and 2 million years ago. This initial eruption produced blocky flows of andesite lava, generated pyroclastic flows which traveled towards the north, and constructed a new volcanic cone. Over the next 80,000 years, Rainier erupted at a very high rate, building itself close to its modern height and emplacing about 50% of the material it has ever erupted. Eruptions during this period constructed the peaks of Old Desolate and Burroughs Mountain. Between 420,000 and 280,000 years ago, Rainier produced very few eruptions, and the eruptions which did occur were generally quite small. During this period, the mountain's summit became highly eroded, with glaciers carving deep valleys on its flanks, much like its modern-day appearance. Between 280,000 and 160,000 years ago once again saw an increased eruptive rate, rebuilding the summit and creating fairly long-reaching andesite lava flows such as what created Kalapache Point. Eruptive activity then decreased again, but between 160 and 40,000 years ago, several north flank vents were created that erupted more fluid basaltic andesite lava flows. The lavas found on Mount Rainier's summit region have been in place since then. Since 10,000 years ago, every single one of Rainier's 23 eruptions have occurred at its summit crater. The largest of these recent explosive eruptions occurred in 250 BCE in an event which was about 15% the size of the 1980 eruption of Mount Saint Helens. While some sources claim that Mount Rainier's last eruption occurred around 1500, there are several reports of grey smoke originating from this volcano during the 1800s, possibly indicating that small phreatic eruptions occurred. The last such report occurred in 1894. While Mount Rainier has not erupted in at least a century, perhaps as much as 5 centuries, it is almost certain to one day erupt again, especially due to the fact that it has produced the second highest number of volcanic eruptions of any volcano in the lower 48 states during the Holocene epoch. As a result of the hazards associated with this volcano and their most recent volcano hazard assessment, the U.S. Geological Survey designated Mount Rainier as a very high-threat volcano. The very name Mount Saint Helens is synonymous for widespread volcanic destruction. While only a minority of people today vividly remember what this volcano used to look like before 1980, that is, a towering, fairly symmetrical glacier-top edifice that earned its nickname the Mount Fuji of America, that would all change on May 18, 1980. On that date, a powerful eruption occurred which resulted in a 2.5 cubic kilometer section of the volcano collapsing to the north in a massive landslide, giving way to a powerful lateral blast which, at a speed of more than 500 miles per hour, would go on to incinerate an area of 230 square miles or 596 square kilometers, incinerating everything in its path at distances of up to 19.4 miles or 31.2 kilometers distant, alongside generating an 80,000-foot-high eruption column and causing a layer of ash to fall across sections of 11 states and parts of Canada. This eruption reduced the height of the volcano by 1,314 feet and left a large northward-facing horseshoe-shaped crater. While this represented North America's costliest volcanic eruption, it was neither one of a kind or unusually large in comparison to prior eruptions, as Mount Saint Helens is not only the volcano with the second highest number of Plinian VEI5 or larger eruptions of any volcano on the planet during the Holocene epoch, but another lateral blast incinerated 75 square kilometers or 29 square miles of the volcano due to an eruption around the year 800. This is why Mount Saint Helens is rated as the second highest threat volcano in the United States, earning a very high threat designation. Even smaller eruptions of this volcano, given the correct set of circumstances, could generate long-reaching lahars which destroy homes, roads, and bridges. And yet, despite its still fairly large size, rising more than 6,000 feet above the surrounding landscape, you might be surprised to learn that Mount Saint Helens is a relatively new stratovolcano if we are talking on a geologic timescale. Eruptive activity at Mount Saint Helens has been dominated by 4 distinct several thousand-year-long eruptive periods where frequent volcanic eruptions occur, only to be followed by 3,500 to 15,000 years of no distinct eruptions occurring. The first eruption of Mount Saint Helens occurred 40,000 years ago, approximately 53 miles east-northeast of what is now Portland, Oregon. In what was already a mountainous region, viscous andesite and dacite lava then erupted, forming a closely spaced cluster of steep lava domes. These eruptions emplaced large amounts of lava, building the base of the volcano. These eruptions continued intermittently for another 5,000 years, the latter stage of which formed the beginning of what would become its central vent. No eruptions occurred for the following 15,000 years until what is known as the Cougar stage of volcanism began 20,000 years ago. The first of these eruptions caused the prior central cone to catastrophically collapse to the south in a massive debris avalanche comparable in volume to what was observed in 1980, filling some valleys with material up to 900 feet thick. This then gave way to a powerful Plinian eruption which distributed ash over a wide area. More lava-effusing eruptions then followed, the last of which produced the most voluminous lava flow in Helens' history, an up to 200-meter-high and 6-kilometer-long andesite lava flow which originated from a still visible vent that, at the time, marked the 6,000-foot-high summit of the volcano. The next eruptive phase occurred from 13,000 to 8,000 years ago via the growth of dacite lava domes that produced frequent collapses, ejecting ash and increasing Mount Saint Helens' height to 7,000 feet. The final eruptive period began 4,500 years ago, meaning that everything above 7,000 feet elevation formed in the time since. Numerous andesite and dacite lava domes were in place during this eruptive period, and glaciers grew on Helens' edifice. Interestingly, despite the explosiveness of this volcano, between the year 105 and 260, 3 basalt composition lava flows erupted from the summit and flanks of Mount Saint Helens, which would go on to travel up to 9.8 miles from the volcano's summit in runny Pohoihoi lava flows, which may have lasted for several months each. The longest and most voluminous of these primarily effusive, although perhaps moderately explosive eruptions, which may have seen Strombolian eruptive activity occur, created what today contains the Ape Cave lava tube. Since 1400, Mount Saint Helens has produced Plinian eruptions in 1480, 1482, 1800, and 1980. Several small lava dome and flank andesite eruptions occurred in between the majority of these, with the last such eruption occurring between 2004 and 2008. Hidden in a series of glacially carved valleys 23 miles south-southeast of Mount Saint Helens in the state of Washington is a largely forgotten volcanic system known as the West Crater. At this very spot, a mere 7,700 years ago, a cluster of highly explosive eruptions occurred, leaving behind not only a gaping 1,600-foot-wide crater at a peak known as Bear Mountain, but also a 2.5-square-mile lava flow. This lava flow was unlike what is commonly seen at Kilauea or Mauna Loa, or even Iceland's Reykjanes Peninsula in the last 3 years. While lava flows from those volcanoes were thin and runny, sometimes moving at speeds of up to 15 miles per hour, the lava flows from the West Crater were incredibly slow-moving, viscous, tall, and crumbly. Today, the remnants of this viscous lava flow stand out against the surrounding tree cover, with its source being more densely vegetated due to the ash it ejected. This is the story of Washington's least-known volcano, which is one day likely to erupt again. The West Crater volcanic complex, despite its name, does not only contain the lava dome which goes by the same name. Instead, it consists of a series of 13 separate volcanic vents over an area of 54 square miles which each erupted once and then never erupted again. The story of this volcanic field began 360,000 years ago at a point 1,600 feet northwest of the Soda Peaks. At the time, a recently expanded zone of weakness had formed linked to the Cascade mountain range, which allowed magma to ascend through the crust. This magma subsequently reached the surface, generating an explosion, and low-viscosity basaltic lava emerged. During what was a brief 4-day-long eruption, 250 acres were covered in a thin layer of molten rock. The next eruption occurred 20,000 years later when magma with a higher gas content erupted 5 miles west-northwest of the town of Stabler. Several 100-foot-high lava fountains were subsequently generated, which occurred alongside intermittent small explosions that ejected ash. Lava flowed out of the ever-growing cinder cone in all directions at a high rate, and due to the low viscosity of this basalt, it quickly created a shield of black lava. As this shield volcano continued to grow, lava was primarily directed towards the south, traveling 13 miles to the Columbia River, where it temporarily dammed it. By the time this eruption had ended 340,000 years ago, 34 square miles had been covered in a layer of lava. Scattered eruptions followed, but by 200,000 years ago, the composition of eruptive products had changed, with all future lavas having an andesitic instead of basaltic composition. These eruptions were still mildly explosive, but created thick flows of grey lava. After 10 vents had been constructed, the area seemingly entered a temporary, highly active period around 8,000 years ago, potentially due to lingering magma left over from an initial intrusion. This magma rose to the surface and produced a Strombolian eruption in 6000 BCE, sending bombs of lava over a several hundred-meter radius, and during a 2-day-long eruption created a 50-foot-high cinder cone on a hillside known as the Hackamore Creek Cone. In 5700 BCE, magma began ascending underneath the summit of Bear Mountain, which at the time contained abundant groundwater. The heat from this fresh molten rock caused the groundwater to flash to steam, build in pressure, until finally it was too great that it cracked overlying rock, generating a tremendous explosion. As a plume of ash rose to a height of 20,000 feet, pyroclastic flows raced outwards, incinerating everything within a 1-mile radius. Heavy ashfalls subsequently occurred, with areas close to the eruption site receiving between 3 and 30 feet thick of ash. This sequence formed the 1,600-foot wide and 475-foot deep Puny Creek crater. 100 years later, another explosive eruption took place, carving out a 1,900-foot wide and 200-foot deep crater. From this crater subsequently emerged a dome of andesite lava, which increasingly grew in size until it overflowed the crater. Over the next 9 months, andesite lava slowly progressed towards both the east and west, covering an area of 2.5 square miles in grey lava. Although the West Crater volcano has not erupted since, it statistically averages an eruption about once every 30,000 years and will erupt again. Future eruptions are likely to be mildly explosive or highly explosive, potentially progressing towards largely non-explosive andesite lava fusion after the initial eruption stage ends. As a result of these hazards, the U.S. Geological Survey designated the West Crater as a low-threat volcano.